Welcome everybody to lecture 11, Databases and Information Systems. In the winter semester used to be 25 and now 26. We are almost done, just 2 more lectures with contents and exercise sheet. So first I will say something about your experiences with exercise sheet 10, I guess. Web app parts 2, demo of some web apps, and official course evaluation, which is already running. I have a slide on that. And today there will be a shift towards some linear algebra, quite exciting stuff, and word embeddings. So the last 2 lectures will be more in the direction of modern information retrieval and not the classical one. And exercise sheet 11, we will talk about this. So first about your experiences with the last exercise sheet. So there were only very few submissions in the single digit. I'm not happy with that. Maybe I say something about it, maybe not, maybe later. So again, very interesting. I'm actually really enjoying the topic and would have liked to spend a lot of time learning this stuff. Note the conjunctive, would have liked to spend. A lot of fun. I'm looking forward to finishing this up. So also the few people who worked on it didn't quite finish. There was some talk about Easter eggs. Let's see. Okay, let's actually see it right now, because let me just show you some of your demos. That's what we promised last time. And here they are. So that's we've selected 3 of them. So that's just how it looks like when you do the exercise sheet. So let's try something. Okay, here we have auto-completion. Let's just, okay, it's not search as you type.
Exercise sheet 9.
We are at exercise sheet 9?
Yeah. But you still have to...
No, it was the submission deadline for exercise sheet 10.
Yes, but that was just a couple of hours ago.
Okay. Okay, we have to do that next time then. Okay, it's not the submissions for exercise sheet 10?
It's for exercise sheet 9.
Let's just do it next time then, okay? I'm sorry. I think this was a misunderstanding. Let's just do it next time, and because it... okay, we just do it next time, next lecture, and we have more time for our stuff. Who's the president of Venezuela? Not the orange hat. I believe that only a new and fair democratic election should answer that question. Can I be sure nobody from the US is reading this answer? Only few answers, because there were only few submissions. So will this be on the exam, all this web app stuff? So there were 2 lectures about web applications. As I've argued, web applications are a super important part of databases and information systems, because most of these systems nowadays are exposed via the web. And if you have worked on the exercise sheet, I mean, very typical, you have a web page, and on the back end side, it's doing exercise sheet stuff. And yes, there's always at least one question, and often more in the exam, that involves writing server code, HTML, JavaScript. And not only that, it requires understanding how this works in principle. And as I've said many times, the individual parts are simple, but putting this all together is complex. And you only learn that by doing it. I mean, learning by doing is a big part of this lecture. So if you have done the exercise sheet, that will be easy. We don't see, and also from experience, how you can learn this stuff without doing the exercise sheets or something equivalent. So, yeah. And for many exams, I can tell you, we always have participants in the exams, also in the oral exams, who make the impression of never having written a web app themselves. It's very easy to find out, and then you don't get the points, or you don't even pass. So please don't be one of them. So if you haven't done the exercise sheet now, you have to do them when you prepare for the exam. Otherwise, you don't learn this stuff. This stuff in particular, you don't learn it by looking at the slides. Especially the web app stuff, you have to do it. So please, if you haven't done it now, do it later. So official course evaluation. instructions. So you should have received an email from this is done centrally from the university. Who has not received this email at least once? The first one should have been from January 12th. Is there anybody? So who has received the email? Let's do the other direct. Okay, that looks good. So this is working. There were always problems in the early times, but this is working now. Perfect. Mail in 2026 is finally working. So please, especially the people in this room who are the selected few who are participating, hopefully actively, please take your time for this. Be honest, concrete, and fair and generous. I should add, generosity is always good. I mean, there are grades, you're giving grades. Don't be too strict. The free text comments are the most important for us. I mean, if you see a grade, it's only the number. You don't really know what's behind it. In the free text lies a lot of information. And they are telling from experience always very interesting for us. So it already runs for a week. It runs not for another full week, but until Sunday. So please do it, sit down for 15 minutes. It's actually fun. Think about it and write something in the fields. So there's one question that's always very interesting for us that asked you how much you worked on the exercise sheet. Maybe you didn't do them at all. Maybe you did some of them. I mean, it's anonymous. You can be honest, and please just say how it is, because that's very interesting feedback for us to know that. It's anonymous, so you can just write. There's no reason not to be honest there. And please do it. It's centralized. Once it's closed, we get the result and everything. There's nothing. We can't get your feedback anymore. So please do it today after this lecture, but at the very latest until Sunday. So it's a one-time thing for the whole course. Really important for us. Also people on Zoom or people who watch it later, please do it. Yeah, and I just asked that question. Also, nobody in the Zoom wrote something. There is a forum where you can say if you didn't receive it or there was any problem, and then we see what we can do. Okay, so shifting of gears today, vector space model. Now for something completely different. And it's just 2 lectures, but at least we want to start with that part. And let me just start with it, and you will see where this is going. So this is our running example for today. And let's just understand this example and what it means. So this is the same as we had for a number of sheets, especially for the first 2 sheets. These are documents. Document 1, 2, 3, 4, 5, 6. And so we have 6 documents, and these are words here, and we are writing this as a matrix. And what does it mean? It's exactly what we had in the first lecture, but just written a different way. This means document 1 contains the word internet once, the word web once, the word surfing once. This document contains the word internet and surfing, but not web and not beach, and so on. This contains web and surfing, and so on. We also have a non-one here. So these are like TF scores. So this means this document contains surfing twice. And let's actually go right in the coding part. Now let's just go here, and let's let me do the following. Let me copy the code we had from the first lecture before I go back from the very first lecture. I just want to show you I'm really copying it. So we will start from there. So what did we have there? We had an inverted index. So we are going back to the roots. We had an example TSV here. Yeah, and let's just look at that again. So just so that you remember. And let's also look at the example TSV. So that was we had doc 1, a movie, a film, movie. And let's just execute it and see. Maybe make this a little larger. And then I will go back to the slides. Python 3 inverted index. Let's first run the doc test to see if this still works. This still works. And then I'm running this with, it's just counting the number of words here. So movie occurs 3 times, twice in document 1, and so on. And let's make a little change here. So we are slowly getting in the mood again. We don't want this part. And let's just change our code a little bit so that we are getting back. So here we have, and let's not call it record ID, let's call it document ID. We're now calling it, whether you call the text things records or documents is a matter of taste. So let's do a few things here. And let's see where else we have record. Here we have, so I'm just doing some renaming here, and you can look into the code while I'm doing small changes. I don't have stuff in the other columns, I just have something here. It's the title, we don't actually need it, but let's keep it. That's the actual text. And so we don't have this part here, we don't have anything in the other columns, so let me remove that. I think we should, no, we don't want I just want to remove the new line at the end, so description and the title I don't need, so I can just do this here. Let's see whether it still works. I did some small changes here. Yeah, that still works, and that also still works. Okay, and now let's let's do our example 2, and let me do a few more things here, and let me make this a bit smaller. So what this corresponds to, so this is like a document which has, and we will work with this. So I need a tab here. So this is internet, web, and surfing. That's our first document. The second one is internet and surfing, and we will work with this thing. So that's why I'm taking some time. That's the second document. The third one is web and surfing. And that's the third document. I'm sorry, this is going a bit fast. Danke, Frank. The fourth document is internet, web, surfing, surfing. The order of the words, like in the first lecture, does not matter, right? We don't store that information. So this is like internet, surfing, web, surfing. And so that's document 4. And then we have document 5.
Isn't there beach as well for document 4?
There's also beach, you're absolutely right. So let's just do it like this: internet, web surfing, and beach surfing. Yes, let's do it like this. And then I have document 5, which is about beach surfing. And document 6 has the same words, and let's put them in a different order, just to make that. So this is exactly our our document collection. And let's just see whether we also get something meaningful if we run that here. Yeah, that works. So we have the word internet 3 times, the word web 3 times, surfing 7 times. Let's just check that. 7 times surfing, 1, 2, 3, 4, 5, 6, 7. So it's like adding up the counts in these rows, gives you a total number of word occurrences and so on. Also note another thing which is important for this example. There's like internet and web kind of mean the same things. They are so-called synonyms or almost synonyms. And surfing has a different meaning depending on the context, right? You can be surfing on the internet or surfing on the beach, the same word meaning different things in different contexts, and that's called a polysem. And let me just write that on the slides, and that will be important later on. So internet and web, that's synonyms. And that's synonyms. That's very important in language. That's what makes searching hard, right? You have many different ways to say the same thing. And also the same word can mean different, and that's a polysem. So depending on the context, it means different things. Okay, that's our running example. I think it's clear enough, and kind of the simplest example, which contains all these thingies. Each row corresponds to a word, each column to a document. These are the scores. Also note it's a matrix. I could also put other scores here, right? I could put PM25 scores or whatever, and that's what you should do for the exercise sheet. Here it's like term frequencies. Okay, if there are no more questions, we will just move on. So, writing a collection of, I think we have to close the door, thank you. Writing a collection of documents like that, we do that in a break. Writing a collection of documents like that, it's called the vector space model, because you write things as vectors and the whole thing as a matrix. And that's called a term document matrix. Terms are in the rows, documents are in the columns. How do you do retrieval? So you can also write your query as a vector now. So query is now 010, so that's like the query web surfing. And let's just do that, and let me go to, let's just compute the dot product now of the two, and let me do this as follows. So let's first take this vector here and this vector here, and let's just take this as vectors, and you tell me what the dot product of these two vectors is. Just four-dimensional vectors, this and this. And let me briefly explain dot product while you're thinking. Some of you will know this. So if I have two vectors and one is x1, xm, and m here is the number of terms, and y, and y1, and ym. And then the dot product, we always write it with a big dot, because it's not multiplication of numbers, but of matrices. Then this is the sum of the pairwise products. So what's the dot product of these two vectors? Yes? 2, yes. 0 times 1, 1 plus times 1 plus 1 times 1. So very simple, and let's also do it for the, so that's 2 here. What is it here? Dot product? 1, yes. Here? 2. This one? 3. This one? 1. And this one? 1, yes. And these are exactly, if we would have done retrieval like we did in lecture 2, this would be exactly the scores, the TF scores of the documents. You just sum up the TF scores of the keywords of your query, right? Web and surfing twice. In particular, we would get this document here, would get the highest score, so we would rank it first. And this document here wouldn't get a high score because, we asked for web, but there was internet in it. So that's the word mismatch problem. Any questions about this? Otherwise, I will move on. Simple stuff so far. Nothing is really hard today. And let me... So what we just did, we did pairwise dot product computation, and now here's one important thing to understand. I can compute all scores in a single operation using matrix vector product. And you should have all learned linear algebra at some point. Maybe you have forgotten it, so let me show you something very basic in case you don't know how matrix vector multiplication works. Let me just show it to you once. It's also simple stuff. So let me write the vector like this. This is our Q. So this is Q, and let me write it like this. This is our Q, and it's a 1 times 4 matrix, right? A vector is a special case of a matrix. And when I write this bar times something, it's number of rows and number of columns. And let me write the matrix to the side of it. So that's here. And let me just copy it. 1, 1, 1, 0, 1, 0, 1, 0, 0, 1. And what I'm getting at is that this is a matrix vector product, gives me all the scores. 0, 0, 1, 1, 0, 0, 1, 1. Okay, and this is now the matrix A. And this is a 4 times 6 matrix. And how linear algebra works, that's very simple. If these two are compatible, then the multiplication works. So in this case, this 4, this is the wrong color, sorry. This 4 must match this 4, and then I can do the multiplication, and then the result will have which dimensions, please? What are the dimensions of the result here? I will get a result vector. 1 times 6, yeah, exactly. That's how it works. 1 times 6. So here I will get something. So that is now Q, and I'm making Q as a column vector here, but here I'm transposing it. You write that as Q transpose times A, and this is now a 1 times 6 vector. And this is actually here, it's the Q transpose. So transposing is if it's a 4 times 1, so this here is actually, this is a 4 times 1 vector. When you transpose it, you write it as a row. And let's just briefly see how matrix multiplication works. So now I get 1 times 6, so that's wrong. It is 1 row and 6 columns. And how does it work? Well, it works like this. Let's just do this in, so you take this here and you just compute the individual dot product. So I compute this with this, and this will be the first component here, and I write it there. And the same would work for, so you compute, if it's a matrix multiplications, you just compute all the dot products of row on the left side and column on the right side. And so here we would get, let's just write it down. What do I put here? What's the first component of the result? 2, yes, 2. And then it's just like, let me just do that again with another color. Now I take the same here again and multiply it with this one, and the result is 1. 1, and then I go on like this, and this is again 2. Let me write it in some other color. This is 2, this is 3, and this is 1, and this is 1. Is that correct? And that's how vector matrix multiplication works, right? So in the general case, you could even have multiple rows here. You would just compute all the possible combination of a row on the left side with a column on the right side, and this gives you the matrix on the right side. And in this case, it's a particular matrix. It's a matrix with just a single row. Any questions about this? That's basic, that's how linear algebra works. And the point is, the big point, I get all my scores with one matrix vector multiplication. And now we want to put that into code. And this is the basis of, this is like the basis of everything you do in machine learning as well, because you do a lot of these things. And now I want to show that this is very much what we did in lecture 1 and 2. You can just do the same thing in linear algebra. So let's just go back here and do that. And let's let's turn this into term document matrix now. And please pay attention and work with me. So first, words I want to store the individual words, and words, that's I think it's a list of strings, right? And this is initially empty. I also want a term document matrix, so I somehow need to know how many words do I have and how many docs do I have. And initially they are 0. I'm in a constructor here. So I need a little warm-up. And let's do the following. So word in words. This is the special case. I hope you remember that code. It's not too much. So this is, I'm seeing a word for the first time. So if I see a word for the first time, and I want to give word IDs now as well, right? What I want to do is, I'm not sure whether I have. So this should get the ID 0, 1, 2, 3. I need to assign them to rows. Oh, and actually, let's just check. And I will just, the word I encounter first will just get the ID 0, the word I encounter second. So let's just make sure I encounter them in that order in my... Let me just do that. And so I will encounter internet first, web second, surfing third. So that's fine. And then beach, I think that will work just fine. And let's just do that here. So... So if I see a word for the first time, I just words append. No, that should be self words, right? Self words append the word. And now I do the usual stuff here. And in the end, I should know the number of words. Is just, that's just how many words I have. It's also the length of the inverted list dictionary. And the number of docs is... Robin, since we have a break, maybe you can set up these demos with the JavaScript version in the meantime. Maybe you can try it, and then we could do it after the break. Because we have the submissions, maybe it works. So we have num words and num docs here. And let's just look at this code here. Let's not print the term frequencies, but let's just print the inverted lists and see whether it works. And I'm deliberately taking some time here because we did this several lectures ago so that you get back into the mood. So now I'm just, I did the same thing, did some renaming, removed some columns, and counting the number of words and docs. And I'm doing it with our new example, docs not found. So how do I get the number of documents? That's not right. From this code, how do I get the number of documents? Yes? Doc ID. Doc ID is very good. Yeah, I'm counting up the doc ID. Is it doc ID? Doc ID plus 1. Very good, because we are starting with 0 and we want a number. So that's a classical one. You want a number of something, you have some ID which you increase. Very good. So, and let's just also print the number of let's just print the number of num words and num docs. Self is not defined. That should of course be II here. So it's a 2. Okay. So maybe I was. Why do we have 7? It's only 6 documents. I said it should be doc ID plus 1, but I'm slightly confused. Why do I have 7? Did I? Yeah?
Can we start by 0 and then increment it before we can encounter the first word? So
Yeah, these are one based.
Yeah, they are one base. So I made a mistake and you were right.
have a second issue with the
Yeah?
words.
Thank you.
In line 48, we use words, but words is the result from direct kind or
It's self words. Yes, and here it should be. Thank you very much. That's why we're doing it. So now it's 4 times 6, which is the dimensions of our term document matrix. So and now we do the following. We just take the code from here, and now we construct the term document matrix from that. So how was our function here called? It was called build from file, and now we do build term document matrix, and let me term document matrix from that. And what do we do? Build a term document matrix from an already built inverted index. So, and now we do something new. So now we need linear algebra stuff. We need a data structure for a matrix. Of course, we could do that with array of arrays, but let me go to so how do you do linear algebra in Python? So we use PyTorch. That's what you use for all the machine learning stuff. In the past, we used NumPy and SciPy. NumPy is kind of the historic package, but still used for basic linear algebra. You have vectors and matrices and so on. You want to multiply them, do all this stuff. And then there was SciPy when you do more sophisticated stuff with matrices. So this was just linear algebra for whatever applications. Most frequent application is machine learning, and for some years now there is PyTorch or Torch, which provides all the linear algebra stuff and also geared towards machine learning use. So PyTorch is huge because machine learning AI is huge, and for this lecture and for the next one you only need some very basic things, which is why we have prepared some a cheat sheet for you. So if you go to of course there's the whole documentation, which is like, there are functions for any number of things. But what you need here is like create a matrix with only zeros or an empty one, or a matrix with only ones, or multiply 2 matrices and so on. You don't need a lot for the exercise sheets, but you should understand basic Torch. That's one of the things. Understanding PyTorch or Torch and doing basic algebra in Python is something you should learn for this course, and it's something you need anyway, I think, for whatever you do also in other lectures. So it's a very useful thing, and also relevant for the exam. So you import Torch. First you have to install it. That takes a long time. So you install the package with pip install Torch, and then you prepare a meal or dinner or 2-hour lunch, depending on the machine. Can take some time. I already did that here. I hope I did that here. Where's my virtual environment? Okay, maybe I have to get it from there. Now I'm worried. I hope I have. Let's just do import Torch, and let's just see what. Let's first do that and see what happens now. No module name Torch. Oh my! Can I just copy a virtual environment here? I hope I can, because I have it somewhere. Do I have it here? No, I don't have it here. Maybe I have it. Have some code here. No, where's my virtual environment? Oh, now I'm worried, because installing Torch takes a really long time. I tried this yesterday.
It's way faster with you. It's way faster with you.
No,
the problem is that we are on a network file system here, and there is.
You wrote comma.
I wrote comma. Thank you. Oh, now I'm a bit worried that I'm code lecture 11, and now I should have a venv here. Okay. So will it work if I copy a virtual environment here? Missing destination. Okay, even the copy takes a long time because it's so Python virtual environment. Even the copy takes a long time, let alone installing it. Torch is like everything you need to know for machine learning, everything. So it's, yeah. Yeah, let's just, on this nice winter afternoon, we patiently work for just even copying the installed packages via network file systems. Take a long time. Let's,
Question.
yeah, sure.
Do you know any nice CLI tools that show progress for copy?
Nice command line tools that show progress. I'm sure there is one, or you can.
Yes.
But this is, I'm amazed how slow this is. You are getting some coffee. That's water. Yeah. I mean, I'm amazed how long it takes. In the meantime, let's just write some code. So while we are installing Torch, so I create. How do I do it? I want to create. First, let's think about it. Why this is installing? How do we now turn this inverted lists? And you saw it here. Why this is still. Is this waiting for input or is it actually doing something? This is crazy. I think let's just hope it will end. This was our inverted list. And here's something important. So we can just go back to writing code. Keep this in your mind. That's the inverted lists we have computed. So internet is contained in documents 1, 2, 4, and they were not zero-based. That's just how we did it. Now we want to turn this into a term document matrix. So let's start as follows. So I start with a zeros matrix. And I'm not sure whether it's zeros or zeros with E or not E. And that's the dimensions we already have. So it's self num docs like this. And now, well, I would say we just go over our words in order. So for word ID, word in enumerate. We have our words, right? So first time we encountered internet, that's word 0, web, word 1, surfing, we have that in self words. So I want the word, because I need the word to look it up in the inverted lists, I also want the index. So let's self words, maybe that works, okay. And now is there a problem with that code?
Maybe to avoid confusion, we should also start the word ID at 1.
We should also start the word ID at 1. Yeah, but we don't have, now I'm getting them from enumerate. I could rather start the doc IDs with 0 to make it. But let's just go from the code we have, but it's a valid. And now now we're getting the first word, and now let's go over the doc IDs in the inverted list. So for the first, now let me iterate over 1, 2, 4. So for doc ID in self inverted lists of word. So now we have word, and we also know the word IDs from this enumerate. And now you think about what should go in this line. In the meantime, this is not. Come on. This is.
You could try just to copy the byte version of the full.
No, but it's a virtual environment just for that, what I installed. Let's just see whether. No, I don't want to. Let me just. This is amazing stuff. Let's just go to public code. Let's see whether anything is happening at all. So where are we? We have venv is there. You can just see how many bytes it copied. 4.9 gigabyte. And let's see, okay, we learned something about. Let's see how big the internal thing is and whether we are. And I really hope that that you can copy a virtual environment internal, because otherwise we will have to install it. Lecture 11, Venv. Okay, now I'm doing, okay, we are making progress. It's just said Torch is 7 gigabyte, yeah?
We just activate the virtual environment from the other directory and then cd into our current directory and run the file.
Wow, that's all another, that's what we'll try next. So we are getting some good ideas here how to solve this embarrassing situation, but we are, okay, network file system is like the bytes are carried from the one to the other. It's like incredibly slow. While we're patiently waiting for this and maybe trying your hack, what should go here? What do we want here? So inverted lists, think of, let's write this code. Yes?
So now the word ID and doc ID describe the exact position in the matrix?
Yes, the matrix, yes. So I want to, so what do I put here? And I can write it like this in A and then row, comma, column. So what should be the core? So at which, I have now a word with a word ID and a doc ID. What's the point in the matrix?
Word ID and document ID minus 1?
Doc ID minus 1, yes, because they're, yes. Okay, and let's just do the following. I set it to, let's just do it like this. That was already good enough. So let's just say there is a word in that document, right, at that position. So let's just put a 1 there. And let's continue to write code while our virtual environment patiently copies. I think it's nice because it keeps some suspense and we don't know what's, I mean, this is just amazing. This is just, so you are saying go there or just,
I think you can also source it from the current directory.
I just source, let's just try that. Let's just source.
That means that you will have to pull it from the network share, which was the easier.
Yeah, so let's just do source. I mean, now I'm just, so bin activate. That's what you are proposing, right? So we have a virtual environment. Let's just try. Now I'm, I mean, it's really exciting stuff. Okay, it's doing something. So here's, oh, it's always doing this. Oh, NumPy is also not there. Oh my. Now I have to, let's just ignore this. So what's this? Huh? That's just, yeah, it's a warning, but let's just grab that away. I don't want to see it every time. Grab minus NumPy is not installed. Okay, and CPU, okay. So we have some, yeah, you see some sophisticated, well, what's there? CPU conversion. Yeah, it's just some error messages. I could install NumPy, but I'm afraid that will again take a long time. I'm just removing these error messages. So this is just standard error to standard out so that the grep actually works. So that's just, yeah, so this is our, okay, this worked. Let's print our matrix. Let's print our matrix and let's first print an empty line and now let's print our term document matrix A and let's print it A. Let's see whether that works. A is not defined. Why not? I think I should return it here. And first of all, so let's just return it here. And if we return it here, we should, what's this matrix? Here's another thing. It's a tensor. So in Torch, very briefly, you have vectors, matrices. So a vector is something one-dimensional, a matrix something two-dimensional. You could also have something three-dimensional, right? Rows, columns, and something else, like a cube, four-dimensional. So the general term for this is tensor. Vector, matrix, 3D matrix, 4D matrix. It's mathematically, it's nothing, it's simple. So everything is a tensor in Torch, and so let's just get that from here. So that's just building the getting the, and let's also, torch has no attribute zeros, so I'm assuming it's without an E. Yeah, that looks good. We have our, and now it's showing tensor, 1 point, that's ugly. Let's change that in a second. But we do get, this resembles our matrix we have already seen, right? And please do this for you have to know torch, you will have to write torch code in the exam. I can guarantee you that. Let's have a nice function, print matrix. I mean, this is so ugly. And torch, for all its sophistication, does not have a function for printing a matrix nicely. So let's just, so this is a torch tensor, and let's just print it, print a 2D, print a matrix nicely for lecture 11. So let's see, what do we want? We want one row for row in A. Torch is nice in that you can do the obvious stuff. So this is a matrix, had rows. We can just iterate over the row, and let's just do the following, print. What do? Let's do something like this. Take the individual columns. Let's see whether and I want to print each value as, no, let me, okay, what do I want to do? I want to do 0, 2.0 f, maybe 4x in row. What do you think? Could that work? So I'm just, for every row, I'm taking the value, printing each value with exactly 2. This just means 2, no digit after the dots. We'd only have integers for x in row. Could work, right? What do you think? I forgot a space. Where did I forget a space? I certainly forgot the closing bracket. You think it's wrong?
The problem is the type notation, so the tensor should be uppercase, I think.
Thank you. Anything else? Thank you for paying attention. Okay, and now I should actually call my method, right? Print matrix. Wow, such a beautiful matrix. We are getting there. So, this, I hope you have seen it so many times on the slides now, is almost our, where's the difference? Can you spot the difference? There's only ones. How do we get this 2 here? Let's go back to our code. How? We actually want the term frequencies, and we have written this code, which is not, so somebody else. How do we get the?
In the inverted list for every word, we also need to the document which has the word the count, like the term frequency.
Yeah.
Of how often the word appears.
So we need a term frequency, but given the code we already have, how can we modify this code to get the actual counts? Yes?
Instead of the equals, maybe a
Plus equals. Yeah. I mean, think about it. We are going through these lists, and this means there's inverted in document 1, there's web in document 1. And so each entry in one of the inverted lists here is one occurrence of a word in some document. And whenever we do that, we just say, in the respective position in the term document matrix, increase the entry by 1, and we are starting from 0. And then we get what we want, exactly. So this, yeah, and now we have exactly our matrix. And now, I think we have all the foundation ready, and it even worked. And thank you for so even the Venv suggestion works. I'm sure it's still copying. Yeah, it's still copying, of course. It's so funny, okay. And let's move on. Now let's, why does this even compile? Okay, now let's, so now we want torch, tensor, I'm never sure how exactly. Now we want our query vector was 0, 1, 0. Is it like this? And it's now an array of arrays. Let me move this up. Oh, this is not what I'm not sure why that happened. I'm sorry. So, is this correct? Maybe I'm creating a concrete tensor now from an array of arrays. This is just one row, but it's still conceptually an array of arrays. Let me just print that here, and let me just also print the query vector v, print matrix q, and another empty line. That's fine. Let's just print that. So that's now our query vector. That looks good. 0, 1, we didn't have to write anything else here, but I do have some. Okay, I don't need another empty line here. And now we just want the scores. And how do we get the scores? Now we just multiply, and we already wrote q as a row vector. I didn't write it as a column vector. So now I just do q transpose. This is already transposed here. Multiply, and you just write it like that. You can. There are also functions for this. This is just the matrix vector product. And this is big. And now let me write this. So these are now the scores. I mean, this is simple stuff, but it's actually pretty deep. And let me just write the scores now. This is also matrix now. And let me just print an empty line so that there is some space to the next. And let's just see that. Yeah, and these are our scores. And now we have actually done something big. This is a toy matrix now with 4 rows, 4 words and 6 documents, but the very same thing would have worked for 10,000 words and 1 million documents. So with a single operation, I've computed all similarities of the query to all documents at once. And now I could take these and sort them and get the top ranked document. And that's exactly. Let me just show you that to you, what you should do for exercise sheet 1. For the exercise, oh yeah, that's the evaluation. You get, since you don't get points here, you just get karma points. So this exercise, so please do that. It's apt to get into the mood of using Torch. As you can see, as you saw, it's actually very simple, but you need a conceptual switch in your mind, understand about linear algebra. Do the same thing. So you take lecture 2 now, exercise sheet 2, where you had BM25 scores, you turn them into a matrix, and then you just, it was your first little search engine for lecture 2, you do the very same thing, and then you make sure that everything is just the same. So you're not actually adding features, you're doing the same thing just with linear algebra. And you will encounter some interesting problems and which will help you understand things. So let's move on here and think about whether you have any questions. This is what we see. Here we even define the, I mean, in the code we computed it from the inverted list. You can also define it explicitly. This is just defining a tensor. Should this be a capital T? Yes, right? No? It doesn't?
It should be, but not the function.
Oh, the function. Okay, thank you. So this is how we, yeah, this is what I said. Tensors, 1, 2D, 3D. Okay, so here's some more stuff. So yeah, 20. That's how we did it. BM25. I mean, now we had term frequency scores. Yeah, and if you just put other scores there, you will get exactly the same ranking as in lecture 2. I already said that. That's this exercise sheet. Now there's another way how to compute document similarity, and that is using the cosine similarity. And let's talk about that. That's how you usually do it. So here we just had this 0, and that's important for the rest of the lecture. So now we just took the dot product of the two, and this gave us the traditional scores. And So cosine similarity between, let me just show that. So now we consider these things as vectors. And let me just, let's see a few things here. Let's just see a few things and read the slides in the meantime. So let me, so if my x is x1, comma, x, and let me take n as an index here, and y is this. Let me just write that again. y n, let me write that again. X times y, that was just, I will just write it again. xi times yi. What is the, so this here, that is just the sum of the squares of the individual components and the square root of that. That is the norm of a vector. And this is actually the same thing as multiplying the dot product of the vector with itself and then taking the square root of that. This is just how it's defined, and this is just by definition. Let me just do it that way. And so if you view these as vectors, let me just write them. So x is a vector. You can write them as a vector in a high-dimensional space, and this is another vector here. And then this thing here is the there's an angle between them, and the cosine similarity. So what do we have here? This is So why is this called? I mean, there's no cosine here, right? And no angle here. This is just a definition. This is how you would compute it. You compute the dot product and you divide by the norms of the two vectors. But this is actually equal. Let me just write that here. This is exactly equal to the cosine of alpha, which is the cosine of, writing it the same way, the angle between x and y. So this thing here happens to be equal to that. And I'm not sure you can, I think I will skip it now. You can prove that this is equal to this, but I don't think it will give us much insight now, so I will just skip it. You can prove it from this one. This is just the law of cosines. So if, let me just show you one thing here. So if the angle between A and B is 90 degrees, then what's the cosine of the angle? What's the cosine of 90 degrees? 0. And what do we get then from here? If I have, so this is, if I have here, so that's A, B, and C, and this is the angle here. What is this saying if the angle between A and B is 90 degrees? Yeah?
Square root of, C is the square root of A, so this is 0.
Yeah, this is then, this is 0, yes. And what do I get? What's written there then?
This is Pythagoras.
Yeah, that's the Pythagorean theorem, exactly. So this is 0 if AB is 90 degrees, and then is this theorem, the Pythagorean, I think that's correct, theorem. And I'm not proving, you can, this is a nice exercise to prove it. So let me just write that here, proof exercise. Nice exercise. Yeah, this proof here that x times y over y. So if you like mathematics, that this is actually exactly the cosine of the angle between the vectors x and y. So we are only computing with this. So actually it's just compute the dot product and divide by the length of the two vectors, and we have divided length here, but this is actually equal to the cosine of the angle, and that's why it's called the cosine similarity. Everybody calls it the cosine similarity, but it's actually just a dot product between vectors. How do we compute the cosine similarity? So you have to compute. So now we want to compute cosine similarity between vectors and not just dot products. So we have to divide by this. And the problems, and you have to do that for the exercise sheet. And you also want to do that with a single matrix vector multiplication. And the annoying thing here is that you have to compute this norm, and this is like computing the dot product with itself, taking the square root. That's kind of expensive if you have to do that for every... So what you do, and that's very important optimization, you normalize the vectors once in advance, and afterwards you can just compute dot products. And let's just see that here. So once in the beginning, I normalize all vectors to 1. And how do I normalize a vector to 1? I just divide it by its length, and then I have a vector of unit length. And if the vector has unit length, then this is just 1, and this is just 1, and then I can just compute the dot products like I've seen on the previous slide. Let me just show that here. Let me just check that nothing else is here. So what's the length of x prime? The length of x prime, if this is x divided by x, then this is just the norm of some vector times some constant. That's just, I can pull that out, and that is just 1. And the same thing, of course, for y prime. That's also 1. And let's just do so y is, what if I do x prime, if I compute the dot product of these, then this is just, we can just plug it in. This is just x over x times y over y, and this is just x dot product of x and y, divided by the size of the two vectors, which is just the dot product, which is just the cosine similarity, yes. So that was just, that's just how we define the cosine similarity of the angle between x and y. So then we can so we normalize the vectors 1, and then we compute the cosine. And then we just, by computing dot products between the normalized vectors with a single matrix vector multiplication, we get all the cosine similarities. And I think we will do that after the break. Is there any more question now about what we had so far? There's not too much stuff left. Any questions for now? Otherwise, let's just have a break and continue in 10 minutes. Okay. Come back, let's continue. And Robin thankfully managed to set up the demos for the dynamic case. So let's just switch back to that and show some demos for 5 minutes, and then we resume. So here I showed 2 of yours and then the master solution. So here's one. My amazing, awesome, all good, very nice search engine. So let's, pretty good. I mean, that's pretty responsive. That's already quite, so let's just write Arnold. People never write how to, Arnold, I'm misspelling it totally. And let me just emphasize one thing again. So let's go to Wikidata, which we have seen, and they have also a search, and let's just, I do Arnold, if I type this, but if I They don't have error correction. We have, I mean, that's nicer than what one of the biggest websites of the world does. And you did it with just a few exercise sheets. And also here it has it's actually very good sheet. So you do show relations, and now it's doing a Sparkle query for that entity based on, and the Sparkle query was realized by translating it to a SQL query, and we had a database for that. So this little web app's combining everything we have done in the previous lecture. I think that is pretty amazing. And I'm amazed at how responsive this is. So and it's searching everything is in here. That's 100 million entities it's super responsive. Let's see, Freiburg, University there. Okay, but it's working really well. And here's one more thing. There was a Okay, I typed the matrix, and now I get some funny stuff. So for those of you who did the exercise sheet, you encountered this, hopefully. So what's going on here? I type the matrix, I get the matrix as a result, and I get this. Before I go into that, let's just show another one. That's another one here. Let's also do the Arnold query. Let's see if I just reload it. Robin, it's trouble finding. Is it the wrong one, or can you start it again? Sometimes it's... We just wait patiently until Robin restarts. Does it take a long time to restart? Should be there. So that's Proot, one of our machines, 9992. Search HTML. It was working. We wait patiently. What? Yeah, restart it. Restart it. We wait patiently. How did they get the pictures is one question in a Zoom chat. How did you get the pictures? Is the person who made this here and can answer the question? Yes?
I got it from
It was you. Congratulations. Yes? You got it from?
the Wikipedia files within the image section.
Yeah, there was, in the input files, there was a column which gave the image files, and you can just load them, and they are loaded lazily, right, in the background. Yeah, so it was actually part of the input file, one column, and then you could. So actually, when you do this, getting it to start at first, there's a lot of things to get right, but once you have it, all the foundation, you can actually do a lot of things pretty quickly, and this is an amazing website. So is it? Yeah, it's there. So let's try so that's also very snappy and also works. I also have the triples here. So I'm amazed at how fast it is, even with Python, because there's stuff in Rust, and it's amazing. And let me show you also the master solution, and let's see whether that works. That should be service unavailable. That might be because I actually have to start it first. So this is working with I talked about this, the global interpreter lock, which somehow makes multi-threading in Python impossible or very hard, and this is just a version where you don't have that, so it's building the QGram. It's just the master solution now. And let's see a few more. We wait patiently so here you see Python, so it's building the QGram index. That could be faster, but I think it will be faster than copying the virtual environment with Torch, which probably is still ongoing byte by byte. Or maybe the two are now interfering. Probably they are. We wait patiently.
Maybe we should wait faster.
Just a joke? Okay, there it is. And let's go to so I've just, let's see how Yeah, there it is. Fuzzy data, that's our master solution. So let's, that also works. And now let's look at a few more so that you see all the Easter eggs. Oh yeah, that's a nice one. Snow. So now it's, let's remove the, yeah. So what's going on here? Let's just try to understand. We have our browser control. I'm going a thing here. So I'm typing snow. You see, for every, you get a lot of stuff here on the right side. Let's just see. I mean, that's, yeah. So if I go here now, I mean, it's snowing on the left side. We look at what's actually happening on the right side. And here's the, so this, yeah, we are getting a JSON from the server. You understood? Here's the first hit is snow. Or let's Himalayas, it's the second. So we get description, mountain range in Asia. This is the second hit here. Oh, it's hidden. I have to shovel some snow to see it. Himalaya description. This looks all good. What's happening for snow? Description, oh my, what's going on? Image, that's the description. The description is actually, you see, the description, it's a bit small here. It's actually an image tag which loads an empty image, and when the image is loaded, it executes some JavaScript and loads this snow.js, which you see further down here. So it's loading some JavaScript, it's loading an empty image, which after loading loads. That's a hack which still works in modern browser. And then it's actually loading some JavaScript which is executing arbitrary code. So that's called code injection. So you did think nothing about it. In the data set you're using, the nice, beautiful data set we prepared for you, there's actually stuff that can get triggered and then execute. And let me just show you the other ones. And yeah, that was this one. It's just, yeah, so there's just injection, code is being loaded, doing arbitrary stuff, and the stuff can really be, there are a few more, and then we go back to embedding. Oh yeah, here's asteroids. Now we get a little spaceship, and of course spaceships, 80 styles, they can also, isn't that amazing? So now we can modify our web page. This is so cool, I think. And what else do we have? Let's type gorilla. Okay, now we have a video game, a whole video game. Okay. Now we can play a video game. Okay, oh wow, do you know it? Okay, now I can throw a banana at the other gorilla. Let's see if we hit them once. 50. I have a throwing angle. What velocity? There's a wind speed from going in some direction. Let's just try something. Angle. Now I'm okay. Oh, wow. Wow, it's amazing. It's amazing. Okay, now we have a video game. Our website disappeared, but we can reload it. And here's the. Does it work? So who remembers this from, do you know, it's an old internet meme. Yeah. So in case you don't know the meme, look it up. So that's what I hope you will remember code injection for the rest of your life now. It's pretty powerful. I mean, you just read some data set, and the nice thing here is it works most of the time. It's only triggered by, and that's also how clever code injection works, right? It's not obvious, it's hidden and then can be activated by, in this case, just by certain queries. And you have no way of finding this out if you're using a huge data set. I mean, you're not going through it and checking every individual byte. So I think I unshared now with, and let's go back to the lecture. So, code injection. Where do I go? Now we have half an hour, but we don't have too many slides left. So, back to profane stuff. And thank you for the nice web apps. The few of you who did the exercise sheets built. Back to our code. So here we had our term document matrix. Now very important to understand the relation. So let me say it again. This term doc, this representing things as vectors, matrices, that's the foundation of all of machine learning. We started the lecture with inverted index and simple search engine, which is how you did it 20, 30 years ago. It's actually the same thing in a certain way, and I want to explain that now to you. And it's simple, but it's deep, and it's important to understand. How do you store these matrices? And it's the same in machine learning. You have these huge matrices. This is a toy example, but let's just assume, and let me write some numbers here. Let's just assume I have, number of terms. So number of words or terms as they are called. Let's just assume I have 1 million words, and let's just assume I have 10 million documents. Then the matrix, dimension of the matrix is size of matrix. Size of A is now 1 million times 10 million, which is, what is it? And let's say what is it? 10. What's a million times a million? It's a trillion, it's not a billion, it's a trillion. So even if I just use 1 byte per entry, I already have 10 terabytes. If I use 8 bytes, I have 8. It's huge. And I mean, that's just 1 million times 10 million. That's small. We have already worked with more than that. So you never store it that way, but it's very typical that most entries are 0. Here it's a toy example. I have a few 0. I mean, there are a lot of words. An individual document only contains a very small subset of the words, right? It doesn't contain most of the words. So most of the entries will be 0, and it's like that in machine learning. So how you actually store the things, you store them in sparse matrix representation. So you store only the non-zero entries together with their row and column index. And this is again very... So for example, so let me just put this in blue here. So that is now, and now it's 0 based, 0, 1, 2, 3. And let me write the columns in orange. So this is 0, 1, 2, 3, 4, 5. So what I have here, so this means, this is just the entry here in row 2, 0 based, and this is column 3, 0 based here, which means it's this entry here. So that's how you actually store these things. That's how you store in sparse matrix representations. You just list all the non-zero entries and you say, in this row, column, there is this value. That's how you store it. It's very simple. And now, here it comes. And now the question is, do I store it row by row or column by column? That depends on the application. Typically, it's stored row major, so store row by row. And now look at this. If I just, the sparse row major representation of a matrix is just, it's exactly the inverted index, right? What is this? This is now everything in row 0. And what is row 0 in my matrix? That's just all the documents containing the word internet. So internet 0, it's just a non-zero entry, so it's document 1, 2, and 4. Which is what I have here, or 0, 1, and 3, if it's 0 based. So this here is just the inverted list for internet, right? It's just the same thing. Clear enough? That this is the inverted list for, and then I'm also storing the So that's just the 0 is just the first word, so internet, and the orange ones are just the inverted list for internet, and these are the term frequencies here. Any question about that? Yes?
Is there still like hardware accelerated way to calculate cosine similarities then?
Whether there's a hardware accelerated way to compute cosine similarities?
Yeah, by hardware I mean GPU, for example.
So that's an important question. So what we established here is that to compute cosine similarities, you have to compute the dot product and divide by the length. And if you divide every vector by its length before, you don't actually have to compute the length of the vectors anymore. So it's just dot product computation. And dot product computation means you can compute all the scores with a single matrix vector product. And this is what all this is. Let me just show that briefly to you. If you wonder why this company is the biggest company in the world, that's because they're selling hardware which can compute matrix vector products very, very fast. That's what GPUs are doing. That's what NVIDIA GPUs. They can do this operation here very fast in hardware.
But can they still do it for a sparse representation?
They work for a sparse representation. That's specifically what they are good at. That's the whole point. So the matrices are almost always sparse. If they are dense, it's not really about computing them fast. They are just too large, right? I just showed you that. These matrices in machine learning and in information retrieval are never dense. They are always sparse matrices. So let me say it more specifically.
In machine learning models they are. In deep learning models they are.
Okay, it depends. It depends. You have not so big dense matrices, and sometimes you have big sparse matrices. Yes, you're completely right. So both cases are important. And this company is one of the most valuable companies of the world, because it builds hardware that can do this very fast. Does it answer your question?
Yes.
Okay, thank you. And thank you for clarifying that you do have dense matrices in machine learning. Okay. And sparse matrices in PyTorch, just for the exercise sheet, you do it like this. Yeah, you just say, you can create it from a pair of row-column indices and the values. You can just look it up when you do them. So you actually hand it to the torch sparse tensor thing as 3 separate arrays. So all the values at the non-zero positions, the row indices and the column indices. So this here is 1 triple, which says row 0, call 0, value 1. And the COO is just coordinates. The naming in PyTorch is a bit strange. PyTorch is great. The one bad thing about it is that the naming is not really how you would name it if you understand linear algebra. The naming is very much tuned towards the machine learning applications, which is quite confusing at times. Calling the row major representation of a sparse matrix COO for coordinates is just weird. Anyway, yeah, and then once you have that, you can always do this in PyTorch. Any questions about this part? Now the last part, which is embeddings, which is very simple and nice, but important, and second part of the exercise sheet. So what we have for our toy example, we had 4 different words: internet, web, surfing, beach, and words can, and we also had that in the first exercise sheets, first lectures. You call the set of distinct words of a document collection the vocabulary. So for our running example, it was this. So we can give those IDs. That's already what we did in our applications, 0, 1, 2, 3. We just did it in the order that we encountered them. We could also do it in a different order. So not really important, but we have to stick to it. So whenever we encounter internet, it's 0. We have seen that a lot of times, that you want to work with IDs in the actual code. So here's something called one-hot encoding in machine learning. And now I'm introducing a few terms from machine learning and what they mean in the information retrieval world. So one hot encoding, I want to represent a word as a vector now. And I can just do that as follows, by just, and here's the example. So in our toy example, we just have 4 words. So I represent every word as a 4-dimensional vector, and I just put a 1 in the position of the word ID of the word. So all my words are now 4-dimensional vectors because I have a vocabulary with just 4 words, and I put a 1 here and a 0 there. So this is called one hot encoding. You have n different things, you want to represent them as n-dimensional vectors, you just put a 1 in one place and a 0 at the other place. And so it's trivial, and what do I get? I now get pairwise orthogonal vectors. And we will extend this in a second. This is called one-hot encoding. And one-hot because every vector has a 1 in one position, a 0 in the others. This is nothing special. And this can be done for any ordered set. You have any set of a certain size, you can represent it that way. And that's a common thing in machine learning. Now, how is this one-hot encoding related to what we have seen so far? So if I have a document, internet, web surfing, beach surfing, that was one of our documents. I think it was document 4. Yeah, it had internet, web, beach, and surfing twice. It was our document 4. This one here, 1121, that's our 4th document. This is the document, and I could it's actually, if you just look at the column here, it's 1121. And what is this? And the query vector is also that. Okay, okay, I'm sorry. I just wanted to, yeah, it's written up here. So this document is just the sum of the one-hot encodings of the words, right? If I just sum these up here for these words here, so I have, let me just do that. It's also trivial. So I have the word internet here. So internet is there once, then I have web there once, I have beach there once, and I have surfing there twice. And if I just sum these up, then I get a 1 here, I get a 1 here, I get a 1 here, and I get a 2 here. So a document is just the sum of the one-hot encoded vectors of the individual words. So yeah, that's how the two are related. And some obvious properties. So 2 different words, it's like they are orthogonal. You take any pair, they are orthogonal. And now the last 2 slides introduce embeddings. So that's how we did it so far. So 2 different words are just orthogonal to each other. Wouldn't it be nice to give every word a vector with the following property? Like if the words mean a similar thing, then these vectors have a higher cosine similarity, so a higher similarity than words that are dissimilar. And this is exactly what word embeddings do. So word embeddings also give a vector to each word, but with nicer properties. So now the dimension can be larger. So it does not, and actually we now have for the exercise sheet 11, we will give you vectors for words which are 300 dimensional numbers. And we will give you vectors for 129,603 words. Every word gets a vector, but it's not a one-hot encoded vector. It's a dense vector, dense of 300 dimensions. And they are not pairwise orthogonal. They now have exactly that property that if you take internet and web and you compute the dot product or the normalized dot product, the cosine similarity, it will be high. If you take internet and beach, it will be not so high. And let's just write code for that. That's the last code we write today. And let's just, I've prepared a little bit of code here. So here are the, so I store the, sorry. So this is just the PT file here where I store them. That's just a serialization. That's just a dictionary from words to these 300-dimensional vectors, one for each word. And I'm just loading them here. Yeah, that's just trivial code for argument passing. And then I'm saying torch, load this file. And let's just run that. Embeddings test. It's just a simple test. Oh my, I have to do my little magic here to get rid of the E grep minus V of, what was it? What did I? NumPy. I could have, and conversion. I just want to get rid of. The following arguments are required. That's actually valid. I need an. This needs the embeddings file as argument, and let's take the, so fast text, that's from Facebook research, these word vectors, they are nice, simple, and not so many. So torch takes some startup time, and now it's reading the okay, now it read the vectors, loading embeddings from, and we are not doing anything with them. So this is just a dictionary. So let me just do the following. Let's just do internet embeddings, and let me not call it's now the embedding of internet. I could call it internet embedding, but let me just do the internet. Okay, I'm not sure why that happened. And web, that's web, and I had surfing. Let me just do surfing here, and then I have beach. Okay, and now let's just compute the cosine similarity, and let me just show you how simple that is. Cosine similarity between, and let's start by internet and web. And this is the last thing we do. Internet and web. Let me just, I think it's on the slides how I compute them. Yeah, it's torch cosine similarity, and the dim 0 is, yeah. These are one-dimensional vectors now, but you still have to say, compute the cosine similarity in that dimension. So let's just do that. So it's torch dot cosine similarity between, and let's start by internet and web, comma, and I want to compute it in that. Yeah, so please do the sheet and let's just see. So now I get some, and the cosine similarity, it's the cosine of the angle, so it will be a number between 0 and 1. Let's just see what happens and if it compiles. We wait patiently. Okay, we forgot a colon here, so it's tensor. Yeah, it's just one value, but everything is a tensor in torch. So yeah, we don't mind that. Let me just put a. Okay, let me just do a few more cosine similarity. Let's also do internet and beach. They should be unrelated, right? And let's also do beach and surfing. They should be somewhat related. Yeah, and let's format that. Okay. Let's just run it, and let's maybe have a bit more space here. So I'm now computing 3 similarities between 3 word pairs, and it's really, I'm just taking the vectors, and so what do we see? Internet and web. What is the cosine similarity between 2 vectors that are orthogonal to each other, where the dot product is 0? What's the cosine similarity? It's 0. Why is it 0? If they are orthogonal, I have 2 vectors which are orthogonal to each other. Why is the cosine similarity 0?
They're not similar.
Yeah, but why is the cosine? How's the cosine similarity defined?
As the dot product defined by the...
Okay, yeah, it's the dot product. It's 0, and it's also yes.
So mathematically it's 90 degrees and cosine.
Yeah. So you're both right, exactly. It's the dot product is 0 because they are orthogonal, but it's also the cosine of the angle. The angle is 90 degrees, and cosine of 90 degrees is 0. So 0 means not similar at all, and 1 means the same. Cosine, if it's 0, it's 1. So here we see internet and web, 0 points, that's pretty close to 1. Internet and beach, that's significantly lower, beach and surfing related. And so it's hard to say, are these good numbers or bad? So we also prepared for you random. Let's just give every word a random vector, and let's see what happens then. So it's exactly the same. Every word gets a 300-dimensional vector, but it's random. And what do we see now? Yeah, now we see random vectors are very dissimilar to each other. Now we don't see So we actually see this desirable property, internet and web, they're related to each other, and the vectors are actually pointing in a similar direction. So small angle between them. Beach and surfing also not quite as high, but also, and internet and beach are much less related, and we see a smaller number here. And and now you can do the exact same thing, and it's surprisingly simple and effective. So we just carry. So for the one-hot encoding, that's how we did it so far. What we did so far is like summing up the one-hot encoding of vectors to get our documents. And now you can just represent documents by summing up the embedding vectors. So they don't look like this, but 300-dimensional and dense. But otherwise you do the same thing. You want an embedding for the document, you just sum it up. And let's see where that gets you. That's the second exercise. Yes?
Can you go back?
Back, forward, which slide number? 15, 4, 16? You forgot. So no? No question? Okay. Yeah, and that's what we just did. So to get a vector for a document, just like we did before, you just sum up the... Yeah, you can just sum up these vectors, then you get another vector of the same dimension. And to give you the opportunity to buy some NVIDIA stock, but also you should have bought NVIDIA stock. I mean, then one worry less, right? Just to say it again, these guys build hardware that does matrix multiplication fast. It's exactly it, no more, no less. Here's the exercise sheet. Exercise 2 is... Yeah, you just embed documents as the sum of the embeddings of the words. Just do it and play around with it. And it's a very simple idea. It's amazing how fast it gets you. And then we have prepared some movie plots for you. It's a relatively simple exercise. Please do it. So let's see. We are almost in time. We are in time. Any questions? Let me also check the chat. There's just one more lecture with contents next week. Yes? You remembered the slide number?
Well, no, but generally about the vector space model.
Mm-hmm.
So the query cute cats eating and eating cute cats have different semantics, but they would be represented equally, right? So
everything. So what were the cats eating dogs or dogs eating cats? Yeah, it's a different semantic. Everything we did so far, we ignored word order. That's correct. I mean, you could this is something we talked about in the first lecture, also store the position and then give a boost when words occur next to each other. But yeah, so far we completely ignored word order, and that takes you pretty far, but it's a simplification, exactly. So in this whole lecture we ignore word order. Is there another question? Yes?
Then, if my math intuition is right, then the cosine similarity measures the alignment of two vectors.
It's whether if the two vectors are exactly the same, the cosine similarity is 1, because the angle is 0 degrees. If they are orthogonal, 90 degrees, it's 0.
So I could have two embeddings
Mhm.
that point in exactly the same direction,
Mhm.
but one is very, very far away and one is 100.
Oh, they are all 0 based. The length doesn't matter because they are, for the angle, it doesn't matter how long they are.
So the length of the embedding vector don't have any meaning.
The length of the embedding vectors, that's very important, don't have any meaning, and that's why you divide by the length here.
Yeah.
So the cosine, so it doesn't matter, which is why in the beginning you can just normalize them so that they all have the same length, and then you don't have to divide them by the length anymore. The length plays no role. It's very important. Any other question? Yes?
What lecture will you do the next semester?
The next semester? The next semester or the next year?
Next semester.
So in the last lecture in 2 weeks, I will talk about all that, about the future. But very briefly, I will do programming in ++ next semester. In a year, so in the next winter semester, it will be the continuation of this one, where we go deeper and do much more machine learning and natural language, so the more modern stuff. So in a year, there will be this continuation, the fortgeschrittene, advanced part of this lecture. Any other question for now? So thank you, do the exercise sheet, and see you next week. Bye-bye.